Hello, and welcome to the podcast Intermolecular Forces Notes, Hydrogen Bonding, and Dipole-dipole. Traditionally, these two are taught together because hydrogen bonding, which is an IMF, is a type of dipole-dipole. It's just a strong one. So when you explain hydrogen bonding and dipole-dipole, you're going to use the same explanation. The same forces are involved. Everything basically is the same, except for with hydrogen bonding, it's a much stronger IMF. So let's actually explain dipole-dipole first, and then we'll explain how hydrogen bonding is a little bit different. So we're going to go ahead and start with the dipole-dipole interaction. And we've already seen this in a lot of our activities in class because dipole-dipole and specifically hydrogen bonding is what we see with water. Okay. So with dipole-dipole IMF, it's going to occur between polar molecules. And these, obviously, if it's a molecule, it's a covalent compound. And the reason why it's going to be between polar molecules is because they have dipoles. And if we remember, those are the positive and the negative partial charges. And it can't just be for the bond polarity, the overall molecule must be polar in order for it to experience the dipole-dipole interactions. So I have down here SO2, which is a polar molecule because there's an electronegativity difference between the sulfur and the oxygen, and it has a bent geometry. So, and the electronegativity difference is greater than 0.4. Oxygen is the more electronegative one. So if we remember, the arrows would have been drawn down here. I'm actually going to erase these after I draw them because we're just going to have too much stuff in the way, but it would have pointed down to here. And then that would give the oxygens the negative dipole, and the sulfur then would be the positive dipole. So I am going to label these. So this has a negative. And so this is usually what we draw when we're showing IMFs. We don't usually include the arrows because it's just too much to look at. Well, if we look down here, I have another sulfur and oxygen, so SO2 again. And this is still polar, obviously, it's the same molecule. So I want to label this the positive dipole, this the negative, and then this the negative. Well, if we have negative over here on the oxygen, what is that going to be attracted towards? And we saw this in our activity where we looked at the water molecules, right? Because water is also polar. So what we're going to see here is an attraction between this negative end of the dipole and the positive of another molecule. And one of the things we have to remember with intermolecular forces is they're not within a molecule, they are between the molecules. Even if they're of the same type of molecule, both of these are SO2s, it's not within one, it's between many of them. And so if we were going to do the dot, 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 or dash, dash, dash over here to represent the IMF, to represent that attraction, we would come over to here, and when we draw the next SO4, since this is an oxygen, that's going to be attracted to a sulfur, and the oxygens are going to be here, and the lone pair, I got to circle that in there, okay, on top of the sulfur to show its bent geometry, okay, and it really doesn't like to let me draw lone pairs, but there are lone pairs here, and here, and there we go, they're kind of little, but we can see them. And so these are going to exhibit that same attraction. And this is what is going to happen throughout the entire substance. And we would obviously have millions of these. We're representing it here with just 3 of them. And those dashed lines are representing your dipole-dipole. So these dashed lines are your dipole-dipole interaction. So this is a lot like an ionic IMF in the sense you have a positive and a negative end attracted to one another. The difference, there are 2 big differences. First of all, it's only a partial charge, so obviously it's not going to be as strong as an IMF. And the second is because it's made up of larger molecules, and it's not just cation, anion, cation, anion, cation, anion, it's not going to have the same type of structure. So it's not going to have that uniform structure like a lattice structure will. But what's really important to always show here is orientation. So you always want to show an oxygen attracted to a sulfur. And what you want to avoid is if you like take the dot, dot, dots and like draw them all the way over. Like what you wouldn't want to do is show like this oxygen dot, dot, dot. Okay, I'm going to draw this and erase it because this is what you don't want. because they're not oriented towards each other, not going to feel the force. So you want to make sure that any IMFs you're showing the dashes towards, that those two things are pretty close to each other. They're the closest things to each other. So I'm going to erase those dash, dash, dash. And we're going to take a look at another example. Okay, so I have another example here. This is OF2, which is polar because it has a bond electronegativity difference of 0.5, which would be polar. And the dipoles do not cancel since it is a steric number 4 bent geometry. And so if this is a polar molecule, the more electronegative one, which happens to be the fluorine here, they're going to get the negative charge. So I'm figuring out which side is the negative side based on which one is more electronegative. So it's always a good idea to keep that chart handy for this unit. Okay. And so since these have electronegativity differences, that makes the molecule polar. And if the molecule is polar, then this negative side here will be attracted to the positive end on the oxygen, dash, dash, dash. Okay, and these dashes over here are representing our dipole, IMF. And it's very important to be able to draw and illustrate these. The other thing that's really important is if we bring another one over, we make sure again that we get the orientation correct. So I'm going to drag this over. And when I do, I want to make sure that this oxygen here is lining up with that fluorine. And so that when I do my dash, 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 I have proper orientation. And we can go ahead and label this with a positive and the negative on the fluorine, because it's more electronegative again. And again, you could do more and more and more of these and keep going, but this is the IMF that is present in these polar molecules. So how can you tell if something has a dipole-dipole? In order for it to have a dipole-dipole, the molecule must be polar. So that's why being able to analyze the structure from Unit 2A is so important, because in order to know whether something is polar or nonpolar, that's going to tell you a lot about what type of IMF is present within that molecule. All right, so the next one is hydrogen bonding, which is a type of dipole IMF. So it's still a positive dipole, negative dipole, attracted to one another between the molecules. What's special about this is it's the strongest of the dipole-dipole intermolecular forces. And this will help us to explain, for example, why something with hydrogen bonding may be a liquid at room temperature, but something with only dipole-dipole may be a gas. Or other properties such as a higher melting point, higher boiling point, stronger, higher viscosity, things like that. And so the molecule must contain NH, OH, this is not the neatest handwriting here, but FH would be the other one. With the H directly attached to NO or F. So it can't be somewhere else in the molecule. So I'll show you some non-examples of hydrogen bonding in just a second. So I have water here, which is a classic example of hydrogen bonding. We see that it has the dipoles labeled positive and negative because oxygen's more electronegative. And okay, if I bring over another one of these waters, so right now they're gases, right? Because they don't contain any IMFs, and for some reason it thinks it's a somehow the FH is coming with us. But anyway, we're going to keep dragging this over. So the positive end will be of hydrogen will be attracted to the negative end of the water. So what makes this hydrogen bonding and not dipole-dipole is the fact that you have an oxygen directly attached to a hydrogen. This makes this a hydrogen bonding hydrogen, and that it's being attracted to another oxygen. So all three of these things are required. This is your hydrogen bonding within the molecule, and that it has to be going towards another oxygen, nitrogen or fluorine as well. And so, okay, if I bring this one over, okay, this hydrogen here is also going to be a hydrogen bonding hydrogen because it's attached directly to an oxygen. And when we bring this next one over, hold on a second, I'll get rid of that little squiggle I accidentally drew. When we bring this over, okay, This hydrogen is being attracted to this oxygen. And we're going to do our dash, dash, dash. And so these dashes, okay, would represent hydrogen bonding. A special type, a stronger type of dipole-dipole IMF. And that word bonding can kind of confuse us. It is not a bond. It is an IMF, okay? So now let's take a look at NH3 as our next example, and then we'll look at some organic and then some non-examples. Okay, so our next example is NH3, which is a polar molecule because the bonds are polar and the dipoles do not cancel in a trigonal pyramidal geometry. And I have the dipoles labeled here. Nitrogen is more electronegative, so it gets the negative dipole. And so when I bring one of these, again, right now it's a gas because there's no intermolecular forces present. When I bring one of these over, I'm going to drag this over, the nitrogen would be attracted, the nitrogen side would be attracted to the hydrogen side. So just like dipole-dipole, the interactions are going to go. The only difference is that, and I want to do my dash, dash, dash to represent the IMF. The only difference with this is that it's a little bit stronger, or in some cases it can be a lot bit stronger, when it is a hydrogen bond. And this is a hydrogen bond because you have nitrogen and hydrogen covalently attached within the molecule, creating the conditions for hydrogen bonding, the super strong dipole. So this is a hydrogen bonding. So in the next screen, we're not actually going to show all of them as hydrogen bonding. It's not the best end. But I'm going to look at which molecules have hydrogen bonding and which ones do not. Okay, so here's some molecules. Let's evaluate whether they have hydrogen bonding or not. So if we look at this first molecule up here, it's an organic molecule. This would not have hydrogen bonding, even though it contains hydrogen and it contains fluorine, because they're not directly covalently attracted. It doesn't create that large bond electronegativity difference that creates hydrogen bonding in the first place. So even though this would be a polar molecule, this would not contain hydrogen bonding. So this would be purely dipole-dipole. If we look at the next molecule here, again, you have oxygen and you have hydrogen, but they're not directly connected together. Again, this would be an example of something that has dipole-dipole, but not hydrogen bonding. Again, let's look at this, and we have a nitrogen and we have hydrogen, but since they're not directly covalently bonded together, you don't create that great electronegativity difference. And therefore, you will have dipole-dipole, but you will not have any hydrogen bonding interactions. So just because something doesn't hydrogen bond doesn't mean it can't be dipole-dipole. It just is not hydrogen bonding, so it's not the super strong one. Let's look at the molecules down here. Now, part of this molecule, this is an alcohol, these hydrogens over here cannot hydrogen bond. So I'm not crossing them out because they don't exist. I'm just crossing them out because they can't hydrogen bond. And the reason why is because they have a direct connection to a carbon. So those are not hydrogen bonding hydrogens. Not all hydrogens hydrogen bond. They have to be directly connected to an oxygen, nitrogen, or fluorine. But if we look over here, this OH creates a hydrogen bonding situation. So this will have hydrogen bonding for part of the molecule. Let's take a look over here at HF, and you kind of can't see the dots here. I'm going to make these a little darker. So if we look here, the hydrogen is directly attached to the fluorine. Yes, this has hydrogen bonding throughout. The next one is another example of an organic molecule. So again, the hydrogens attached to the carbon cannot hydrogen bond. So we're going to cross those out. Okay. But the nitrogen and the hydrogen down here, these are going to create hydrogen bonds in this part of the molecule. So this will be able to attract other things that can hydrogen bond or other dipole-dipoles and have the potential to make a very strong connection. So I'm going to do one illustration of the alcohol over here. I'm actually going to make it into methanol, but to show you how this would hydrogen bond in the next screen. All right, so I've drawn the organic molecule methanol. And these are a little bit trickier with polarity because there's sort of two sides to this molecule. So at first we notice that we have hydrogens attached to carbon, and these are not going to be hydrogen bonding carbon hydrogens. The other part of this molecule is if these are CHs, not only are they not hydrogen bonding, they're actually completely nonpolar. So I'm going to take the highlighter and I am going to highlight this part of the molecule right over here with white, because this generally is going to be fairly nonpolar. It'll have a little bit of polarity from the pole of the OH, but we generally will consider this part of the molecule. All CHs in organic molecules we will consider nonpolar. Now we're going to come over here to the OH, and we know that O and H are going to create dipoles. There's going to be a pole of the electrons, the shared pair of electrons, towards the oxygen. So this oxygen is going to have a negative dipole. Make the pen a little bit smaller here. So this is going to be negative end, and this is going to be the positive end. And it's true that this carbon will get a little bit positive because of the pole, the overall pole, but generally we just worry about the O and the H. We just leave the CHs alone. So now this part of the molecule has a very different intermolecular force. And we'll talk about the nonpolar side of this in the next presentation about what we do with nonpolar things. But if we look over here, this side that I'm shading green is going to be a polar side of the molecule. So what happens is when one of these methanol molecules interacts with another, so we're making a liquid, so I'm going to pull one of these over to here. This CH part of the molecule, it's not going to be attracted because it's nonpolar. So what's actually going to have to happen is the molecule is going to have to flip over and see if we can orient this correctly. What's actually going to happen is you're going to have an attraction between, oops, in the wrong direction here. 1, 2, 3, we'll get 3 little dashes in. Between the oxygen, which on this one is going to have a negative charge, and the hydrogen over here. So it's attracted to this hydrogen because it has the positive dipole. Well, if we come over here and attract another one of these, again, what are we avoiding? Which hydrogens are we avoiding when we show this interaction? We are avoiding the CH carbons because they're nonpolar, so they're not going to have an attraction. And we're showing the IMF between the things that have dipoles. So that would be the positive dipole on the hydrogen and the negative dipole on the oxygen. And I'm going to tilt this just a little bit, see if we can get those little hydrogens away. Okay, so we do our best here. So this is the positive dipole on this hydrogen. And we're going to do dash, 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 dash. Okay, and so the interaction that we're visually representing here is hydrogen bonding, because this is a dipole and it's a dipole between the OH groups, and OH is one of the hydrogen bonding pairs. All right, so this concludes our notes on hydrogen bonding and dipole-dipole. In the next segment, we'll talk about the last intermolecular force, which is called London dispersion.